All right, we're taking a look at function representation today. Just kind of recapping what we've been talking about in class. First thing about function representation. Oh, my little tablet's not plugged in. All right, there we go. There are 5 ways to represent a function. So those 5 ways are through a table of values, as a graph of points, as a function rule, as word problem or described in words, and the 5th way is through a map. So we're going to look at some more examples like the ones we looked at in class, and we're going to focus in on moving from certain modes into the other ones. We're going to have a whole day where we practice building the function rule directly, so we're not going to focus on that one as much. We're going to go from function rule to these things and around. We'll incorporate it a little bit, but we'll take a more detailed look into building the function rule. So let's start off with a table. So let's say our table says -2, 0, 1, and 4. So we've got these numbers plugged in, and what comes out is -9, -5, -3, and 3. So here's our inputs and our outputs. We're going to have to create a map. That was a terrible, I'm going to need more space than that. We're going to create a map. We're going to try to describe the situation in words. We're going to try to build the function rule as well. We can convert from any form of function into any other form of function. So if we were to go from the table, it's probably easiest to go right into the map. We're going to list all of our inputs. The order doesn't matter. And then our outputs, again, the order doesn't matter. So usually when I start with a table, I have it like this. And it's really simple because then the arrows are just going to go straight across. That's not necessarily going to happen depending on the outputs or how if you organize. Some people are known to organize this from smallest to largest, and then these as well from smallest to largest. That will make these lines mess up. For me, I'm just going to list it exactly as I see a table. So a map is really just a more complicated table. The words we're going to come back to. Now for the graph, I'm just going to plot these 4 points. So -2, -9, 0, -5, 1, 2, 3, 4, 5, 1, -3, and then we have 4, 3. That's 3, 3. Sorry, knew something was off on that one. 4, 3. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5, 6, 7. Oh, geez. I knew there was some off on that one as well. I thought this was a 10 by 10 graph. Sorry, guys. It's 1, 2, 3, 4, 5, 6, 7, 8. So the 9 is right about here. Sorry, I thought this was one of my 10 by 10 graphs. It's an 8 by 8. All right, so we have our dots. Looks like, oh, geez. We can connect our dots with a nice straight line, so I'm going to do so. And there's our graph. Now this graph is every possible input and output pairing that this rule could have. The dots are the specific examples, but literally I could drop a dot anywhere on this line and I'd have another input and output pairing. Doesn't matter where it is as long as it's on the line. Now to build the rule, Because we see this as a perfectly straight line, we see it as a linear equation. And linear equations can always be written as f of x equals mx plus b. So what we need to find, so we're going to go back up here to our table spot, is I need to find the rate of change. And either from the table or the graph, I need to find my y-intercept. All right, rate of change, I'm going to use yellow here, has us checking how does it change from one row of the table to another. It's also what is our rise over run on the graph. So we're looking at it. Switch over to orange here. This side, it went up 4. Over here, it went up 2. So my rate of change is 4 over 2. We should simplify. I'm going to move myself right about there. Simplify. So this is really 2 over 1. So our rate of change, m, is 2 over 1. So our equation so far says 2 over 1x. And no, we do not technically need the 1 on the bottom. We're just going to leave it there for our notes purposes. B is our y-intercept. So we can find the y-intercept one of 2 ways. The first way is finding what does 0 equal in the table. So if we plug in 0, what do we get? So our y-intercept is right here. In this case, y-intercept is 0, negative 5. Or you look at the graph and you see where does it cross the y-axis? Right there. So it's minus 5. For our word problems, we need to find an independent and a dependent variable that we could use to set up this story. This can literally be anything that we want, but once we make the choice, how we write our word problem is the tricky part. So we'll start off with something simple. Time and feet. So I'm using a distance and I'm using a time measurement. So let's even be more specific than time. Let's go seconds. All right? So when we look at this equation, these two numbers right here, I'm going to use highlighter to help us out. The independent variable numbers has to be with 1, and then the 2 and this negative 5 have to be described by our dependent variable. So for instance, a potential sentence to explain what's going on in this story is, I started 5 feet behind. Maybe we're running a race. So I started 5 feet behind. Notice that I used our unit for our dependent variable, and I used 5, and I even explained why it might be negative. I'm behind. Next thing I need to do is I need to use my 2 over 1. So this is a ratio. So now I need to set up a ratio that's going to relate feet to seconds. So, and it has to be positive. I gain 2 feet every 1 second. And just like that, I have my word problem. Let's practice another one. Let's say we start off with a graph this time. All right, so I start off with a graph. Grab my line making tools here. Put arrowheads on each side because lines go both ways. Like that. Let me change the color so it's a little easier to see. So there's my equation. Once again, we see the graph. The graph is a perfectly straight line, so we know it's going to be a linear function. So, not y equals, we're using our function notation. F of x is going to equal mx plus b. And now we're going to need to go from the graph to all the other ones. So basically, we can make the rule right now if we want. If we want to find the rate of change and the y-intercept, We could go right to a table if we want to find some points. Can't really do the map just yet, and we can't really do the words just yet. So our choice is to either go here or to make a table. For me, it might be easier just to make the rule. So I'm going to have f of x is equal to blank x blank. I'm going to fill in those blanks as we go. Let's go, orange with red, that's not going to show up too well. Let's go purple. Okay, so I see that I have my y-intercept right there at -1. So the backside of this equation is going to have a -1 right here. Because we know that, we get one free point for sure over here in the table, 0, -1. All right, I now need to find one more point in order to just build the equation. I'm going to need 3 more points for the table, but one more point just to write the equation. Literally any spot on this red line counts as a dot. So I could drop the dot anywhere I want on this line. I want to make sure that I put dots where it crosses the grid perfectly. So I'm going to put dots at every spot that I see, and then I'm just going to pick and choose. All right, so I've already used this dot. So let's pick this next one. That's 1, 1, 2, 3, -4. Now I'll pick this next one. That is 2, 1, 2, 3, 4, 5, 6, 7. So I'm at 2, -7. And if I go back one, I'm at -1, 2. So looking at either the table, ROC for rate of change, y_int, so that's 0, -1. We already knew that. Now our rate of change according to the table is 3/1. -3/1, I apologize. -3/1. And if we look at the graph, I go down 1, 2, 3 spaces over 1 space for our slope as well. Again, do not need the equation, the one underneath. So there's my rule. We've already built the table. So now we're going to build our map. Kind of make us feel like Dora the Explorer. I'm the map. I'm the map. So we've got -1, 0, 1, and 2. We've got 2, -1, -4, and -7. Once again, I drew them in such a way where all I have to do is draw the arrow straight across. Again, work smarter, not harder. Sometimes we're not going to be able to get away with that as much. That's our next example. We're going to see that even when we write the order, our arrows are going to be a little bit more jumbled. Geez, crazy. But you don't have to worry about that. Once again, IV and DV. Again, this could be any 2 variables that you want. So let's go, number of jelly beans. I'm going to tell you guys about the jelly bean fiasco in about 2 days. Number of jelly beans. And we're going to have the dependent variable on our mile time. Let's not do mile time. That's not going to make too much sense in a story problem. It would work, but number of jelly beans and our laziness. All right? So it's going to sound kind of stupid, but I have to relate once again laziness with this -1 and this -3, and then number of jelly beans would technically be the rate of change, the bottom number on our rate of change, the run. So this is where that 1 would come in handy right there. All right, so let's kind of write our story. So I start with a -1 laziness level. So right out of the gate, I'm already lazier than the average person. And then I lose 3 laziness levels. So I probably should call this laziness levels. For every 1 jelly bean. So I start with -1 laziness level, and I lose 3 laziness for every 1 jelly bean. So every jelly bean I eat, I get less lazy. Kind of makes sense. Maybe it's a sugar rush or something like that. All right, let's do one more example. Let's say we start from words. So IV, DV. So we start from words. Let's keep it simple this time. Let's say it's minutes. And our DV is slices of cake. So I have 4 slices of cake already. So I have 4 slices of cake to start. And then I'm going to gain 2 slices every 3 minutes. I think I'm just locked in a bakery and I'm just grabbing every slice of cake that I can find off the shelf. All right, so I have my words. The easiest thing to do from words is to go right into the equation. So we've got ourselves our f of x equals blank x blank, because we have our slope-intercept form, mx plus b. So I start with my 4 slices of cake. So this is my starting value. That's my y-intercept. So right here, I've got a +4. Then my next one, it's our ratio, 2 for every 3. 2 slices for every 3 minutes. There's our equation. So now that we have our rule, we have our option to go right into the graph or right into the table. If we use the table, I'm going to take my equation rule. I'm going to move myself again. I'm going to move myself over here. And I'm going to plug in values for x. Because I see a 3 on the bottom of this denominator, I'm going to make sure all my numbers over here are divisible by 3. So for instance, I could plug in, let's say, -3. So I plug in -3. F of -3 is equal to 2 over 3, -3 plus 4. 2 times the -3 gives us -6. -6 divided by 3 brings us to -2. -2 plus 4 gives us 2. So plugging in -3 spits out 2. So I can come over here, 1, 2, 3, 1, 2. So that's one way we could do it. And we could plug in 0, we could plug in 3, we could plug in 6, 9, 12, whatever we want to plug into. We can plug in other numbers that aren't divisible by 3, but we will be dealing with decimals and fractions at that point. We don't really want to do that, so that's why we're picking numbers divisible by 3. The other way we can do it, probably the faster way, is to graph this equation right from where we are. Since we know this is the y-intercept, we know our graph is going to start 1, 2, 3 right here, because the y-intercept is 0, 4. Then our slope, 2 over 3, that's the rise over run of this graph. So starting at this dot, I'm going to rise to run 3, rise to run 3. Starting at this dot, rise to run 3. We could do the exact opposite. Instead of up and right, we go down and left, down and left. We draw our line. And that's one way to do it. Now that we have the line, we don't have to spend the time building the function rule, plugging numbers in, and seeing what we get. For 3, I come over here, 1, 2, 3. I come up to the line. I see that it's at 1, 2, 3, 4, 5, 6. Right there. Then for 6, 1, 2, 3, 4, 5, 6. I come up to my line and I get 8. So we don't have to use the function rule if we have something else to get us that information. Last but not least, of course, is the map. I told you this next example, the map wouldn't be as busy. I decided to go with another linear example instead of a quadratic example. So this one we can still set up and have our lines straight across. So 8, once again, -3 goes with 2, 0 goes with 4, 3 goes with 6, 6 goes to 8. So quadratic, just because I said I would do it, I'm just going to do real quick. Say, for instance, I had my function rule x squared. I had -1, 0, and 1 as my table. If I plug in 0, or I plug in -1, I get -1 squared, which is 1. I plug in 0, I get 0. I plug in 1, I get 1. Our map, -1, 0, and 1, on this side would have 1 and 0. -1 would go with 1, 0 would go with 0, 1 would go with -1. So in different types of functions that aren't typically linear, that's when you'll get more complex maps.